and I think it loaded last night finally. And I haven't even watched it yet, so it might be terrible. I don't know. It's just going to be so much nicer if I can. Let's see if we can share a screen here. Share content. Whiteboard. Sweet. Okay, so I guess it's probably time. Welcome everybody. Good morning. So today we're going to do some trusses. I don't know if you guys can tell or not. I love trusses. I think they're super fun. So much so that years ago, when I was a high school physics AP teacher, I actually taught trusses. I think that was an absolute mistake. I don't think my students understood anything I was talking about. But I did love them. I still love them. I mean, I love my students too, but you know, that was pretty tough. It's an awful lot. You know, I had like one genius student who got it, and the rest of them were like, I don't know what Wagner's talking about. So that's just how it goes. So I think what I'm going to do on this one is, I don't know if you guys have noticed, but there's two ways to do trusses. And well, I mean, you should have noticed by now, but one way is by, I think what they call it by sections, and the other one is by joints. I very much prefer doing it by joints just because it's more fun, but I'm going to work them both ways, and I'll kind of talk about like the advantages and the disadvantages of doing them each way. And so I'm going to just do like the practice 7. So I'm going to pull problems from there. And I'm going to start with the first one, which is, I guess it's just problem 1. And I like this one just because the geometry is clean. What you want in one of these to make it easiest is for the geometry to be kind of regular. When you have like a whole bunch of different triangles, it just kind of gets frustrating. You're like, you know, so much, I don't know, so many sines and angles, you know, sines and cosines and angles to deal with. We don't really want to kind of deal with all that. So, all right, so here we'll do like, did I get that color? Okay, so this is number 1. And I'm going to do this kind of a rough drawing of this. Hey, it's okay. Hey, shut it. Sorry, my dog hates skateboarders. Hey, come here, look at me. It's okay. He's not coming to rob you. You can go lay down over there. Go lay down over there. Dear bed. You're a very good pup, but you're annoying sometimes. Okay. So anyway, sorry about that. So we're going to get this thing, and it looks like this. Okay, so here we go. All right, so that's pretty much what this thing looks like, more or less. Okay, and these things are 2.4 meters across. 2.4 meters, 2.4 meters. And this right here is 4.5 meters. Hey, shush. Okay. There's no need for growling. He's gone. Hey, shh. You're all right. Hey, stop that. He's gone. Hey, get out of here. Other room. Let's go. Go in there. Go on. Shut up. Sorry about that. The pup is now in another room. All right, so now we've got some forces on this.
You're not recording.
I'm not recording?
I don't think so.
I see it recording.
Oh, okay, never mind.
Okay. It tells you guys if I'm recording. I didn't realize that.
Yeah, we get a little note in the upper left-hand corner.
I guess it like to let you know not to do anything crazy because like, you know. All right, cool. All right, so thank you. All right, so we've got a force here. I'm going to do them in red. So this is a free body diagram of the whole thing, I guess. So here we've got, they say it's P, but I'll just call it P. And then off to the side, I'll say P equals what? And in my case, it's 137 kilonewtons. Okay, the number is not important. And then they give joint names, A, B, C. Oh, good, it's regular, D, E, F, G. And then they give you this thing, F has is a pin. So it's got F in the Y and F in the X. Okay, and then G has just a roller. So it's just got a vertical G. Okay, and they always do that. And the reason that they do those two forces that way, you know, they almost always do a pin on one of them and a roller on the other one, is because you can solve for those. Like, because that's, you know, you can, like, if they gave you 2 pins, then you wouldn't be able to solve for it. It would be 4 unknowns. So in 2 dimensions, you need, you know, you've got 3 equations, sum of forces in the X, sum of forces in the Y, and sum of the moments in the Z. And so you need to have 3 unknowns. If you have 4 unknowns, you can't solve it. So, you know, they do it that way on purpose. So regardless of how you want to solve this and regardless of what they want, the first thing you need to do, and you don't always actually need to do this, but sometimes, and I'll kind of show you when, is you need to solve for the external forces. So in this case, the external forces that we don't know are Fx, Fy, and G. Let's see what they're going to ask for ultimately. If I scroll down, they want the force. So this is the given, or I guess this is the free body diagram. It's not really the given, but, and then required, ultimately they want a free body diagram. They want free body diagram for BD and DE, okay? And then they want, so equals what? And then the second part is they want to know what those things are. So they want BD and DE. Okay, so that's what we're going to look for. And we're going to solve this 2 different ways. I just did the free body diagram of the whole thing, which of course doesn't necessarily get you BD and DE.
I have a question, doctor.
Sure.
So now the forces and the bees, are they giving or we have to find them?
Everything that I've drawn just now is given.
Given, okay.
Yeah. So you could probably bring up on another screen question 1 on practice 5 or practice 7, excuse me, and you can see the problem. So this is everything that's given, except, I mean, the only thing that's not given so far is G, Fy, and Fx that are unknown. Okay, and so I'm going to show you the 2 ways to solve this. I'm going to talk about the pluses and minuses of each. Okay, so the first thing we're going to do, because they're kind of pushing us into doing this by sections, is, so if you have 2 ways to do this, and sections, I'm going to kind of, here's the pluses and minuses, and then joints. Okay, so the pluses of sections is it gets right to the answer. Okay, I guess the minus would be you have to deal with moments. Okay, now that shouldn't be a real minus. But with joints, you don't have to deal with moments. So there's no moments here, no moments. And another plus is it gives you everything. So every joint or every member of the, so you'll get every force in the entire structure. Okay, the drawback of this is it can be time consuming because you have to kind of work your way consuming. Okay. So it just kind of depends on what you're doing here. In this case, when they ask specifically for BD and DE, like if I mark BD and DE, so here's BD is right here and DE is right here. So when they tell you that those are the ones they want, then the sections is definitely the way to do it. Okay, because it's going to be way quicker. Now we're going to solve this both ways. But in this case, the sections is the best way because you know exactly what you want, so you should just like go get it. Like why mess with trying to get every member when they're almost telling you which way they want you to do it. So what this means is we've got to do a free body diagram. We have to pick what our free body diagram is. So if I want BD and DE, I can do it just a lot of different ways, but the best way to do it is I'm going to cut it right through the middle of those 2 things, and here's my free body diagram. Like that. Okay, now the twist here is what's interesting about this is normally I would have to solve for Fx, Fy, and G, but in this case I don't have to solve for them because if I draw that top bit, I don't even have to do the reactions. So these are the reactions: G, Fy, and Fx. Okay, but in this case they're not even in my free body diagram, so I don't necessarily need them. So if we do sections, which is what we're going to do right now, what we do is we're just going to draw that thing that I just do, this. And the internal details of all this don't really even necessarily matter. But what we're going to do is we cut the world off here, there. And let's see, we cut the world off here. and we cut the world off here. Okay, and there's a lot of different norms for this, or like, you know, how you do this. And I'm a little bit, I just like to assume that everything is pushing on everything. So I make all my forces compressive. Okay, so that assumes that the rest of the world is pushing on that thing. So that means all these forces, I'm assuming compression. You will see people that will assume tension. It doesn't really matter, just as long as you know that whatever you assume, actually I should do those in red, shouldn't I, to be consistent, that whatever you assume, if you get a negative sign, that means you assumed incorrectly. Okay, so we've got a force here, we've got a force here, we've got a force here. Okay, and we need to name them. So this one is BD. I usually like to do it with the lower letter first, you know, so that it's kind of like alphabetical order. So this one is DE. It just helps me find it when I'm trying to make a list of all the things that I solved for. And then this will be EG. Okay, and then I've got P right here. I'm gonna go ahead and put 137 kilonewtons on it, 137 kilonewtons, 137 kilonewtons. Okay, and there's no weight. So that is my free body diagram that's gonna solve this thing. Okay, and that's this answer right here. Okay. So now we have to we're just going to solve this. And the nice thing about this is we're just going to do this, you know, we're going to do our three equations. Okay, we're in 2 dimensions. So sum of the forces in the X equals 0, sum of the forces in the Y equals 0, and the sum of the moments in the Z around a certain point equals 0. Okay, now hopefully, you know, you guys haven't done this a lot, but there is an easiest equation to begin with here. Can anybody see what the easiest one is? It's going to solve. Yeah, there's 2 easy equations in this one. Can anybody see what the easy equations are?
We always start with a moment.
Why in this case? Do you know why?
No, actually.
Okay, and one of the reasons the moment in this case is really easy is because we can pick a point that's going to eliminate all the forces but one if we do a moment. Okay, but it depends on where we put the moment. Okay, and there's 2 places, there's 2 correct answers to this. Okay, and I'm going to put a dot on them, so, and I'll explain why. So we can choose right here. Okay, because can you see that if I go right there, DE and EG both disappear. Okay, because they both go right through that point. Okay, so then like this is an easy problem from there for the moments. I can also choose this point right here, which is not even on my free body. Okay, because if I go right there, BD and DE disappear. Okay, so my goal here is to pick points where everything's going to disappear except something that I want, right? And in this case, I'm actually going to pick this point right here. And the reason for that is because EG is going to disappear and I don't need EG, right? The 2 things that I'm looking for are BD and DE. So we're going to have EG disappear and DE will disappear in that equation. But BD I'll still get to solve for, which is one of the things that I want. Okay, so it's just like thinking strategically to save some time here. Okay, so what we'll do is when we sum that moment around point E, okay, now remember the Z direction. So here's X, fingers, Y, palm, and that leaves my thumb going upwards and my fingers are curling around this way. So that's a positive Z. Okay, and so now what we're thinking about is around this point E. Okay, so EG has no moment arm. DE has no moment arm because they both go right through the middle of that. BD, okay, here's BD. Okay, and it's got a perpendicular distance of, you know, whatever this is, because you can see that that's a right angle right there. And so that distance, if we look over here, that's 4.5 meters. Okay, so that's 4.5 meters. Okay, and the sign of that is going the opposite of Z. So it looks like it's gonna have a negative sign. Okay, and then we've got to get these 137s, right? And so both of those also have negative signs. Okay, so we've got a negative and a negative. Looks like I ran out of space here. Equals 0. And we've got 137 kilonewtons, 137 kilonewtons. Okay, and its moment arm, if I like kind of dot it and put it over here. So its moment arm is right here. So that's 2.4. 2.4 meters. Okay, and then I've got another one, which is 137 kilonewtons. And then its moment arm, like if I dot it over here, is this distance right here. Okay, so that's what, 4.8. 4.8 meters. Okay, now the nice thing about that right there is we can solve that equation. Okay, so we can go BD equals basically, let's see here, 137 times 7.2. Oh, helps if your calculator's on. 137 times 7.2. Okay, we divide that by 4.5. So BD equals 219.2. 219.2 kilonewtons. And if you do your algebra correctly, this ends up having a negative sign, which means it's the opposite direction the way that I assumed it. So I assumed it was in compression. So BD is 219 kilonewtons in tension, okay, because it has a negative sign. I assume compression, I got a negative sign, so it's in tension. Okay, so then I need to get DE.
Wait,
So the
sorry,
nice thing,
where was the 4.8 coming from?
oh, the 4.8 is, okay, so if we take this 137 kilonewtons right here, and I slide it over here, so now it's right here. Okay, so I'm looking for its perpendicular distance or its moment arm, so that's this right here.
Gotcha.
Okay, so it's 2.4 plus 2.4.
Yeah.
Okay, good question. Okay, so now to get DE, the other nice thing about DE is in this case is, is also comes out of an equation pretty easy. It's kind of hard to see now that I've drawn all over it, but here's DE right here. Well, notice DE is the only unknown X direction force. So we want to solve the sum of forces in the X. So we get DE looks like we assume that it's positive right here. And then we'll get plus 137 kilonewtons. Okay, so that's this force plus 137 kilonewtons. That's this force, and that's all the X direction forces. So DE equals negative, what's that, 274 kilonewtons. Okay, which means I assumed that this was in compression, so it's going to end up being in tension. DE equals 274 kilonewtons in tension. Okay, and that's a nice way to solve it. Questions? Okay, we didn't even need some forces in the Y, which is nice. And that's because we only needed two things, right? So we only need two equations. Sometimes you can't get away with that. Sometimes you might need the third equation. I'm not sure when that would happen, but that could happen. Okay, so that's one way to solve this, okay? Usually when you do these, the first thing you need to do is you need to solve for these things on the edge, okay? These are the reactions, but in this case, we got away with not doing it. So that's good. I'm gonna go ahead and walk through this and we'll solve, let's just make sure I got the right answers. 219.2 tension and 274 in tension. Okay, so we got this correct. The other thing to note, and you know, obviously these are terrible to grade because you can make a mistake anywhere along here and it just propagates through the problem. But don't sweat that too much. That's my job to kind of, you know, dig through your work and find your error. What I should note here too is that if you think about this, okay, if you have something that's, you know, this is your frame, okay, so I want you to try to think in terms of, you know, some, what's the word, intuition. If you're pushing this way on the top of this thing, okay, hopefully you can see that the frame is going to be wanting to bend this way. Okay, I'm obviously exaggerating this. Yeah, well, so hopefully you can see that the frame is going to want to bend this way. So if you imagine that, okay, the forces that we're working with here, all of these ones on the back side here, you should be able to see that they're wanting to stretch. Okay, so there's tension here. It's pulling. Like you could imagine a rope here would be able to work right there, right? And everything on this side is being compressed. Okay, a rope would not be any help at all right here. Okay, so the fact that you got tension in this joint right here should make sense to you. Okay, it shouldn't be surprising if you think it through. Okay, now it's less clear, at least to me, what should be going on in, say, this member right here, okay, which we just solved for. But you know, in this case, it does end up being in tension. But it's, you know, it's the most important thing is, at least for me, is always these sides that are being stretched, that you should be able to like imagine those as being, you know, tensile. Okay, so what I'm going to do now is I'm going to solve this thing. I'm going to solve this thing using joints. Okay, I like this one as a learning. You know what? I'm just gonna. I don't want to clear all. Okay. So in this case, it's definitely better for this one to do this via. I wonder if I can do this with my finger. No, not with my finger. It's definitely better to do this one via sections, and you'll see that in a second. Especially because they only asked for 2 joints. They didn't ask for everything. So I wish I could get a larger eraser head here. Come on, you can do this. Oh, look, you just gotta go faster. Okay. Come on, you can do it. Okay, this is not ideal. You know, a classroom would be a much nicer place for these things. Okay, so I'm gonna erase this thing right here. And now we're gonna go into the world of, well, I guess I'll leave those little marks because this is where we're aiming for. So normally, like a lot of times I'll get into the habit of just solving for these reactions right off the bat. Okay, it's not a bad habit, but in this case, we can get away with not doing it. So we're gonna do, and the reason for that is because we can start at this top joint. Okay, and so here's joint A. And I'm gonna do lots of little free body diagrams. And usually, actually, when I do this, I don't draw little free body diagrams, I just work on my drawing. But for this one, since this is the first time, we're gonna do it. Okay, so here's joint A. And what I'm gonna do is I'm gonna cut it like this. I'm just gonna look at the joint itself. Okay, and so what we're gonna do is we're gonna cut here, we're gonna cut here. Okay. Jansen, you're sending me a chat right now. I can't talk about that right now. I don't. First of all, I can't bring it. I can't bring the chat up. So just, you know, maybe wait till everybody's gone and we'll talk, or you know, whatever, or we'll talk after. But yeah, if anybody has a chat to the general group, just speak up and interrupt me. Jansen, it looked like yours was just with regard to your situation. I saw the first like 4 words. Okay. Okay. So again, I like to assume compression. So this is going to be AB, and this is going to be AC, and I like to go with the first letter. Okay. And then in that joint, we also have this force right here. Okay. That's force P, 137 kilonewtons. Okay. And we're going to go joint by joint. And the nice thing here is because everything goes through this point right here, there's no moments to sum. Okay, there's just nothing really we can do with moments. So what we do on this thing is we say the sum of the forces in the X equals 0, sum of the forces in the Y equals 0. Okay, so in the X direction, we've got 137 kilonewtons. And we've got this AC minus AC, whatever the component of that is in the X direction, equals 0. Okay, that's a little annoying because we're going to have to deal with some angles here. So we're going to say 137 is positive minus AC. And most of you guys prefer to do the, what do we call it? The, what do they call that thing? Most of you guys prefer to like find an angle and work with that. You can find these angles if you want, and we'll go ahead and do that. So a lot of you will prefer to get this angle. So the angle of that is going to be the inverse tangent of the opposite, 2.4, over the adjacent, 4.5. So we'll go inverse tan 2.4 divided by 4.5 equals 28.072. So that angle is going to be the same all along here. So we'll call that angle theta. Theta equals 28.072. Okay. I actually prefer not to do that. I prefer to do sines and cosines. So basically, like here, for example, I want to plug in the, so AC in the X is going to be what? The cosine of that angle, 28.072 degrees equals 0. But this is very ugly to me. I prefer to note that if this is if we've got 4.5 and 2.4, so I can say 2.4, so I can do Pythagorean theorem to get this side right here. So let's see here, let's see, 2.4 squared plus 4.8, or excuse me, 4.5 squared, 2.4 squared plus 4.5 squared equals square root of that is 5.1. So this side is 5.1. So instead of cosine of 28.072, I'm going to do 137. And you can do it with the cosine if you like, but I'm going to do it as the cosine is the adjacent 4.5 over 5.1 equals 0. Okay, to me, that's easier. Okay, and all I'm doing is some similar triangles, really, ultimately. Okay, and some of you will watch Jeff Hansen, and he does that all the time. Like he'll do 3 over 5 if he's got a 3, 4, 5 or something. You'd be like, where did that come from? And this is what he's doing, is he's using similar triangles, which is all trig is anyway. So this comes out to AC equals, either way you use it. If you want to use cosine of 28.072, that's fine too. So we end up with 137 times 5.1 divided by 4.5 equals 155.27. 155.27. That's kilonewtons. And notice it has a positive sign, so that's going to be compressive. Okay, so that means we assume compression, we got compression, we're happy. Okay, so so cool. So now we're going to do some forces in the y, and in the y direction, we've got AB, which is positive, and then I've got plus AC in the y equals 0. Okay, so AB is what we're solving for here. AB plus AC, which is 155.27 kilonewtons, times the sine of that angle, sine of 28.072 degrees equals 0. Sorry, that's a little sloppy and kind of squeezed in there. Okay, so then, so what we'll do is we're going to solve for this, and look, we're going to end up with a negative sign here. So AB equals negative. And again, I can do AB. What I'm going to do instead is 155.27. Son of a. Okay. I should finish that. Son of a monkey's uncle. That's what my old redneck roommate used to always say. I always thought it was wonderful. So the sign is 2.4 over 5.1. Okay, equals 0. Sorry, that's, again, it's getting really crunched in there. And so we can solve for that. That number times 2.4 divided by 5.1 equals 73, negative 73.067 kilonewtons. Okay, so that means AB equals 73.067. That's in tension. Okay, and this one we could just put a C on the end because we don't need to switch the sign. Okay, so it's like, all right, well, that's cool. And these equations are actually really simple. You don't have to think about the angles. I mean, you don't have to think about moment arms or anything like that. So that's the nice thing about this. The drawback is we've just done all this work. I mean, it's not really a ton of work, but we've done this work and we still haven't gotten to our answers. We've solved now for this one and this one, but we haven't solved for this. That's where we're aiming, right? Is in those yellow spots. So so we still got, we still got to keep going. So then what we're going to do is we're going to start, we're just going to work our way down. So here's a joint that we can work on. Here's a joint we can work on. Okay, and so we'll go. All right, it doesn't matter which one we do at this point because we've got what we want going in there. But actually, it does matter a little bit. Okay, so I'm going to do this one. This is joint B. So it looks like this. Okay, so here's joint B. Hello, my rocky dog. You have escaped, I see. Demanding loving. Okay, all right, my pup. I love you. You're a very nice dog. You're a little annoying, but you're a very nice pup. All right, you get 5 seconds of loving and then you gotta go. Okay, I know. I love you too. All right, my boy. So hard to say no when he's wagging his tail like that. Okay, so we're gonna go up here. There's a few different ways to do this. If you're using a computer to solve this, you have to be consistent with signs all the way through in order to make it work. I like to be inconsistent with my signs because I know these answers. So I know this is compressive. So I'm going to say this is 155.27 kilonewtons. Okay. So in this case, I haven't had to do anything weird. The weird thing is I've got BC right here, which I don't know what its sign is. We've got BE right here. Again, I like to assume that they're all compressive. And then we've got this one right here, which is D. Was that? I can't. Oh, BD. BD. Okay. So in 2 dimensions with no moments, I only have 2 equations. So I'm not going to be able to solve this because I have 3 unknowns. So that's problematic. Okay. So this is kind of some things that you have to think about as you work through these. So I can't solve B right now. So what I'm going to do is I'm going to go to C. And you should be able to see that as I work, if I solve C, I'll get BC here. And that will enable me to solve joint B. Okay, so what we're going to do here is here's joint B. And we're going to go, let's see. So we've got this. And we've got this. And we've got this. Okay, and that one's nice because, we've got CE, which I'm going to assume is compressive. I've got BC, which again, I've solved as compressive. And then we've got AC, which I know, I wrote these down wrong, didn't I? Okay, AC is compressive, so we know this is 155.27 kilonewtons. Sorry, this one was AB right here. So go ahead and make that change. And so I switched the sign on that because I know it's tensile. So I'm actually not going to draw its arrow like this. I'm going to draw its arrow this way. It's actually pulling. It's tensile, 73.067 kilonewtons. Sorry, I have no units here. Kilonewtons. Okay, this one, joint C, I can solve. And actually, you can solve this one, pretty simply. Now, what I like here, and this is how I like to do this, is you see this 155.27? Mentally, what I do is I keep track of what that is in X and Y, especially if I've got nice, consistent triangles. Okay, so this 155.27, I know that it's 137 kilonewtons in the X direction. So basically, I have a force triangle here, and it looks like this. 137 kilonewtons, well, like force triangle. Like I have this force and it's on this angle. This just keeps me from having to do the trig over and over and over again. This is 155.27. And this one is 73.067. So this is the trig for that 155 force. Okay, with that angle of 28 degrees, 28.067. And the reason I do this is because I don't want to do this trig over and over again. What happens is if you've got regular triangles and you can do the trig and you're just going to end up with the cosine or the sine of this angle. And you're going to be dealing with these 137s, these 155s all the way as you propagate through this frame. It's not going to be exactly clear because what's going to happen is this P is going to be adding in there. Oh, we forgot that P. That's an important part of this. Okay, so there's an external force right here that we need to take into account. Okay, 137 kilonewtons. Okay, so this 155 right here, I know that the X component of that is 137. I know the Y component of that is 63.067. Okay, because I've already done that trig. And you can do it again if you want to. You can just, put this little angle in here and do that again. What I'm going to do is sum of the forces in the X direction equals 0. Sum of the forces in the Y direction equals 0. Okay, so in the X direction, we've got BC plus 100, well, that 155.27 kilonewtons. Okay, times the cosine of that angle, 28.072 degrees equals 0. Okay, again, in place of that cosine, we could put 4.5 over 5.1, 4.5 over 5.1 if you wanted to, which is the way I would prefer to do this. Or if you wanted to, you could replace this whole thing with 137 kilonewtons, which I recommend because you just already know that that's what's going to come out to. So BC plus that equals 0. And if you solve that, you see BC equals negative 137 kilonewtons. Okay, or BC equals 137 kilonewtons in tension. Okay, so we can go ahead and that is in tension. So 100 equals 137. Oh man, it's getting really hard to do. Kilonewtons in tension. Okay, so I like to go up here at this point and say, okay, well let's switch this. Okay, 137 kilonewtons in tension. Okay, so now we've got to do CE, and we already know what CE is going to be, or is sum of the forces into Y equals 0. And so I've got CE is positive, and I'm going to minus this force right here, the Y component of that, which again I can do 155.27 kilonewtons times the sine of that angle. I'm just going to put theta here because I've got a space problem. Okay, and again, I could use, in place of the sine of theta, I can use 2.4 over 5.1. Okay, or I can make note of the fact that I already know what this quantity is. It's this 73.067. And so I can say CE equals, in this case, I've got a positive 73.067. So that's compressive. Okay. I don't know that we need that CE, but we have it if we need it. Okay. Okay. So now, knowing that, we can go back over here to this B, and we can, we know now BC. Okay, so I want to switch the sign on BC because it's going the other way. So it's tensile. So notice 137 kilonewtons. Notice, and this is common, okay, or notice that these two are equal and opposite because they're part of a two-force member. Okay. So the most important thing is that they're compressive or tensile. So that's key. Okay, now we can solve joint B if we wanted to, and we're just going to do sum of forces in the X equals 0, sum of the forces into Y equals 0. So if you hate moments, this is a really nice way to do this. You can do this once you get used to this. You can do this a lot quicker than I'm doing it right now. But I know you guys haven't worked a lot of these. So once you start working these and you start seeing these patterns, especially if the geometry is regular. If the geometry is irregular, then it's pretty annoying. I think in your homework, I think it gave you one that was irregular, or like the triangles keep changing size. I think it's called like a Howe truss. Man, there are names for these truss patterns. I don't really know those names. Anyway, so in the X direction, looks like we've got this 137 and that 137. So we've got 137 kilonewtons plus 137 kilonewtons. Those are both positive. Notice that BE is going to have to be compressive because it's going to be the only force that's resisting those two, because those two go to the right. So BE has to go to the left. And in this case, we're assuming that. So minus BE, and it's going to be the cosine of this angle. Cosine, I'm just going to call it theta, 28.072 equals 0, because I don't want to mess with that, because I don't want to write it all out because I have a space problem here. So BE then equals what? 137 times 2, so that's 274 divided by the cosine of that angle, 274, and I'm going to divide it by, so I'm basically going to multiply it by 5.1 over 4.5. So times 5.1 divided by 4.5 equals, wait, oh yeah, okay. I was like, wait, did we solve for BE last time? We did not. So we get 310.53 kilonewtons. And notice we've got a positive sign there. So this is going to be compressive. We assumed the correct sign. Okay. And then let's do sum of forces in the y direction. This is getting really messy. Okay, so this does require some paper. So you guys should know, like, I'm a rabid enviro, like politically and emotionally, et cetera, but you're gonna have to waste some paper here. Okay, or you can do it like on a tablet and waste no paper. That's kind of up to you, but this does take paper. Okay, so this sum of the forces into y. Let's see, so we've got 73.067 kilonewtons. Okay, that's positive, that's this one. We've got a BD plus BD, which we're assuming is compressive. And then we've got plus BE in the Y. Okay, so BE, the Y component. And we're gonna go ahead and do that by doing the sine. Let's see, the sine of the angle equals 0. Okay, so you could do it that way. Again, for me, I prefer the sine of my angle in this case to be 2.4 over 5.1. Okay, the opposite over the adjacent. I mean, over the hypotenuse. Or we can use the fact that I know the vertical component of BE is this thing right here, right? So it is 274. Okay, and we can go ahead and do that if we wanted to. Well, it should be 274, but it's not looking like it, is it? Oh, no, sorry. This is the horizontal component. Sorry, my bad. Ignore what I just said. Okay, so we'll do 310 times 2.4 divided by 5.1. And again, you could just do the sine of 28 if you preferred. Okay, that is a really big number. Wait, oh, because I multiplied by 24, sorry. Divided by 10. Okay, and we'll add 73. Okay, so we get BD equals 219.2, 219.20 kilonewtons. Okay, and we always have to keep track of our signs here. This is negative, so that means BD equals 219.20 kilonewtons tensile. Oh, sorry, compressive, because, oh no, negative sign, tensile. Okay, so you can see right there, like, we finally got to one of our answers. It took a long time, or it took more equations to work. Okay, I love the joint method. I think it's totally fun to work my way through a truss, but you can see, like, on a test, like, a lot of times there will be a question that asks for every member. If it asks for every member, this is definitely the way to go. But if it's asking for specific members, unless the specific members you want are like right, let's see, I need another color, blue. If you're asking for specific members that are up here, the easiest thing to do is work joint A. But otherwise, you want to, like, ideally you want to work sections, and the key is to pick your section that's going to give you your answer. Okay, so we just got our first answer, and we've been working on this problem now for several minutes, 15 or 20 minutes or whatever it is. Okay, now obviously once you get into the hang of this, you can go a little quicker. So let's see. So the problem here now is we now have that one. So let's see the ones we have. We've got this one. We've got this one. I think we got this one. We got this one, and we got this one, and we know this diagonal right here. We know BE, right? So we're getting there. We still got it. We're still trying to get here, right? But can we get that one? I think we can get that one if we do this joint right here. If we do joint E now, because we have two unknowns. We have this unknown right here, and we have this unknown on that joint. So we can solve it if we just go to that joint. Okay, and so that's, you always want to think like, okay, if I'm doing the method of joints, I can only do two unknowns at each joint because I only have two equations, X, sum of forces in the X, sum of forces in the Y. Okay, so that's kind of an important, there's algebraic restrictions here, two equations, two unknowns. Okay, and if you do sections, you can have three equations and three unknowns. But of course, you have to deal with moments. That's the third equation. Okay, come on, get out of here, punks. Okay, you guys are I'm erasing all of this. So if I need any of this information, you guys are gonna have to help me. But I think we've moved on, so we don't need AB or AC anymore. Okay, come on, you can do it. Get out of here. You're doing great. Go, 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 go. Okay, all right, there you go, goodbye. Okay, so here we'll do joint E, because I think that's gonna let me solve this thing all the way. By the way, I hopefully, by explaining to you my thinking, you guys are understanding the strategy here. We're always thinking in terms of equations and unknowns, always. Okay, so here's joint E. Okay, and let's see. So we've got G or EG is unknown. We're going to assume, I assume compressive. DE is unknown. We're going to assume compressive. And then we've got, let's see, CE, which should be down here somewhere. Did I not solve for CE? Oh, here's CE right here. So that's compressive. So 73.067 kilonewtons. And then what is this? What BE? Where's BE? BE is right there. Compressive, 310.53 kilonewtons. Okay. And so again, some of the forces in the X and some of the forces in the Y. And we just want to say, well, what are we looking for here? We're looking for DE at this point. This is the only thing we don't need. So I'm not even going to bother with the Y forces. I'm just going to deal with the X forces. So I've got DE. And then I've got plus 310.53. I need the X component of that force. And so that's going to be the cosine of this angle, which we know is 28.072 equals 0. And again, I could use the cosine, or I can use these, I can use the similar triangles. I prefer the similar triangles. You can do whatever you want. So the cosine, the similar triangles in this case is what, 4.8 over 5.1. Okay, or 4.5 over 5.1, excuse me. So you can use that if you want. Or I can use, like down here, I can see BE cosine theta is this. Okay, so any way you want to do this, you plug this in a calculator, you're going to get what I'm going to put right here. So it's basically these two numbers added up. So that's 274. So DE equals 274 kilonewtons. And we notice that it's going to have a negative number. So DE equals 274 kilonewtons in tension. Okay, so this should be 74. Okay, and I assume that matches the answer from the other section. Okay, questions? Okay, hopefully you see the logic here. You see the flow of it. Okay, I personally enjoy these, but they are time consuming, and there's just really no way around that. Especially if you get a really big truss and you're like, okay, I'm really going to have to, there's going to be a lot of joints that I have to work. But so what's going to happen, probably almost certainly on the test, is I'll give you a fairly big truss, and I'll ask you for, and I'll say like, okay, give me a specific joint. I give you kind of, I could sketch something. That would be the idea here. Now obviously with when you're doing the method of joints, there's so much room for error, because if you get one wrong answer, or you like get one sign wrong, it just propagates through and it just kills you. But on a test, like I'm gonna want to make sure that you can do sections and then you can do joints. And so usually, like what I would do on a test, I'd be like, okay, let's create like a really big truss. I could even get ridiculous about it. And then I could say, give me, and let's suppose we've got a pin here and we've got a roller here. And I could say, like, give me, I want to know these two joints right here. If you go by joints on this problem, you're not going to finish the test, right? Because you're going to have to you'd have to start it aside. You'd have to start over here. So if you start over there, the first thing you got to do is you got to get your reaction forces, and you're just going to be working for, as you work your way through, you're going to have to do this joint, and this joint, and this joint, and this joint, and and then eventually you'll solve your problem. But that's just a lot of work. So if you look at this one and you go, you know what, we're going to do sections right here. Okay, you can solve that in like a split second. Maybe not a split second, but really fast. Okay. The other possibility is what I'll do is I'll give you a small frame that maybe looks like this. Okay, and who knows how it could be being supported like this. And then I might say, give me every member. Okay, and if you need all of the members, 1, 2, 3, 4, 5, and maybe there's a load out here. Okay, it's not going to take you forever, but I'm ascertaining that you know how to do the method of joints. So you're going to have to know how to do both methods. You can't just like pick one and decide that I'm just going to do this one every time. But so that's the idea. Okay. So, ideally, if there was an infinite amount of time, I would be like, solve this one by joints, because that would definitely prove it. Right. Or I could, anyway, so that's the idea. So let me bring up another problem and we'll work it. You know what? I think we should probably talk about zero force members before I move on to another problem. So let's see, where is the zero force member one? Okay, if you look at problem 3, you'll see like an irregular truss, and we can talk about that in a second. Let's see. Oh, I hate those. Let's go down. Where's the zero force member one? Okay, maybe it's the last one. Excuse me. Okay, so I also like this one because I'm going to get this a little bit wrong. Okay, and or at least I struggle finding them all. So I'm going to look at number 13, and there's this really complicated drawing of a truss. So if you have it, go to 13 if you can and practice 6. Okay, and I'm going to draw this. I'm going to do a bad job, but I'm going to do my best job, the best job that I can, and hopefully this thing will accept. You know what? I can just clear all drawings. Okay, so here's number 13. Okay, and it's a truss with like a lot of bits going on. Okay, and I want to talk about the zero force members here. Okay, and it's going like this. And the zero force members, identifying them is just something that's going to save you a lot of time. Okay, so here we go. Let's see here. So we're going to go down to here, more or less, down to here, more or less. They don't really give you a lot of the geometry. Just kind of show you that these things are happening. Okay, and there's a force right here, P. And then, let's see, I guess it's symmetric over here. Looks like this, and like that. And then there's one like this, and this. Okay. And this is like one of my weakest suit is identifying all of them. And they want you to identify all of them. And there's 2 of these. And so you'll get a little bit more practice. So here's P. Okay, so this is some kind of big complex thing. Okay, and I'm not going to put any letters on it because I don't want to. It just muddies up the picture. And so what I'm going to do here real quick is I'm going to replace my frame. I'm going to erase some of these things. Like this is a roller. So rollers can only push up. So we're going to go ahead and put a force right there. Come on, you can do it, buddy. Come on, there you go. Okay, there's a force right there. And I could just call it O if I wanted to. It's not important what the magnitudes are here. And this one right here is a pin. So pins can support vertical or horizontal, but they can't support moments. So we'll call this a X and a Y. All right, so the point here, and this is kind of what we're looking for, and I want to make this clear, is we're looking for places where something cannot hold a load. And the reason something can't hold a load is because, I'm going to draw it off on the side. So the number one thing we look for here is something that looks like this. Okay, let's see. So if I draw a joint, and this would be the easiest answer, would be, let's suppose you had a joint that looked like this. Okay, so if you look at this joint, it may not be clear to you because you haven't done this for very long, but if you look at this joint, this is just a random joint anywhere in the universe. Then what happens is, okay, if this is these are all pins, so we know that this is either compressive or tensile, we don't know. But let's suppose the one coming in from the right is compressive or tensile. The one coming from the left, let's suppose the one coming in from the right is to the right, okay? So this one has to come in from the left. Okay, that's fair. But then if there were a force right here, there would be no way for this to resist that. Okay, there's no force back up. So there's a force down and there's no force up. So what's going to happen is this location right here is just going to, like, the forces are unbalanced. So right here, sum of forces in the X equals 0, but the sum of the forces in the Y cannot equal 0 because we only have a force coming in from the side. I mean, from above. Okay, there's no force coming from underneath. So the only way this could happen is if there was an external force right here, which in this case there is not. So this force right here has to be equal to 0. Okay, which means basically this member right here should not be here, right? Like, we just added weight to our frame without, doing anything to, like, it's completely useless. Okay, now in reality, it's not completely useless, but it's close to completely useless. So we try to avoid zero force members. Okay, really what happens here is if you were to put this thing here, okay, and this is kind of a bit of an aside, if you were to put that thing there, what would happen is the frame would actually bend like this. This thing would be like here. And now, if you think about it, these two things, which I drew a compressive over here, would have to be tensile. So they would have a vertical component. If I were to draw this force like this, they would have a vertical component, and these vertical components would counter that. Okay, and that's what would actually happen. But right now, you haven't been taught to deal with the deflection of the beam yet. Okay, so don't worry about that. Okay, in statics, we're going to assume that the beam doesn't deflect, and so if the beam doesn't deflect, this thing has no moment. Okay, this is why, like, a rope, or no rope can ever be truly flat. Okay, what's his name? Jeff Hansen does a thing on this, and a rope cannot be truly flat. So if you string a rope up like this and you're pulling with all your might here and here, well, that's great, but the rope has weight, okay, which is distributed along its entire length. And so the sum of the forces in the Y can't be 0 unless the rope has some curvature to it and the tension's a little bit up. Okay, so hopefully that makes some sense to you. Okay, so the sum of the forces in the Y can't equal 0 unless the rope actually has some bend to it. And in fact, this curve has a very special name. It's called a catenary curve. And I had this life dream of building a tent for myself to go backpacking with that has a cat curve ridge line on the tent, so that the tent will be completely tight. Okay, because if you just do it out of a straight rectangle, there's always going to be like these tensile lines in your rectangular tarp. So you need something a little bit, anyway, that's just me nerding out. Okay, so anyway, so the interesting thing about this is we're looking for these zero force members, because basically you can make your life a lot easier when solving these things if you can identify the zero force members before you work the problem. And so what we're looking for is things that look like this, and they don't have to be X and Y. So for example, it could be on an angle. So like if we look at this thing right here, okay, that looks exactly like this, but on an angle. So if I draw that force like this, and like this, okay, that's this joint in red. Okay, I'm not necessarily thinking in terms of X and Y. I'm thinking in terms of this direction and this direction. And notice if I sum forces in this direction, that can work out, but there's nothing to resist this force right here. So what that means is that this member right here is unnecessary. That is a zero force member. So what I do is I say, okay, well, there can be no force there. So what I'm going to do is I'm going to go up here. I'm going to erase it. Zero force member. It cannot carry a force. So now I'm going to start working through my frame this way. And I'm going to go, well, what about this one right here? Okay, so if I draw that one, okay, note, if I choose my direction like this, okay, there's nothing to resist anything going in this direction, in the perpendicular direction. Okay, hopefully this is making sense. Okay, so this force right here has to be 0 because there's nothing to resist it. So I'm going to erase that one. That's a zero force member. Okay, now there might be a temptation. Well, what about like this one right here? Well, you notice that on that one, okay, so if this one comes in and this one goes out, let's see. So we've got boom, 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 boom. Well, this force could be pushing in, like let's suppose in this direction is one direction, and this is the perpendicular direction. Well, this one could be pushing like that way, and this one could be pulling that way. So it's okay. So we can't erase that one, at least not with any information that we have now. Now we're going to change that in a second, I think, but I'm not sure. Okay, so let's find out. So what I'm going to do instead is I'm going to look at this one. Okay, and if you look at that one, you should note that is this case exactly just turned. Okay, there's nothing to resist any force going this way. Okay, so we're going to go ahead and erase that one. So we're going to go, okay, well, you're gone, you're gone. Okay, this is not a very well-designed truss. That's what it boils down to. Okay, and then we're going to look at this one and notice, well, let's look at this guy. Okay, you notice we've got forces coming in left and right here, you know, for compressive or tension, we don't know, but we've got nothing to support anything going up or down here. Okay, so if this thing had a force in it, it would, there's nothing to resist it in the vertical direction. So we're going to go ahead and erase that one. Okay, so we're kind of running out of forces here. Huh. Okay. And now if we look at this one right here, you know, this one right here, looks like that one's going to go away too. Okay, because it is this drawing exactly on its side. Okay. So nobody's spoken up, so hopefully this is making sense. Okay, so we're going to go boom, boom, and erase that one. Okay, so those are a bunch of zero force members. And then this is of course like a trick one right here because it looks like all the others, but this one has a force coming in, a vertical force. So this force on the truss has to exist, right? Because this one can, like these two can only pull to the side or push from the side. They cannot support that Q. Okay, so this one has to exist because without it, you know, I mean, the Q is there, so we have to have a force there. Okay, there has to be a vertical force to counter this negative force. There has to be a positive force to counter the negative force. Okay, the ups need to equal the downs, as Jeff Hansen would say. Or he says something along those lines. You know, the positives equal the negatives. So in that case, that one has to exist. And it's the same logic like right here. Okay, that one looks a lot like this one right here, except that it's got this external force on it. So we've got a push here. So this has to exist to push against that. Okay, there has to be a force in there to resist it. So this one, even though we want to get rid of it, we cannot. And so that changes things on this side. Okay, so we're going to look for the things that look like they're erasable. So you see this one, that one looks like this. Okay, boom, goodbye, my friend. We knew you so short. Okay, and we can go down and do this one. Notice that one looks like this one, except the force is on an angle a little bit, but that doesn't matter. So we're going to erase that one like that. Okay, at this point, I think we might be getting to the end here. Not sure what else here we can erase. I don't think we can erase this one. I don't think so, right? Because the force, we could have a positive force. We could have a vertical force up here and a force down there, right? So we can't really do that one. Okay, and so even here, like, you know, this is so without doing any math, I can show you some things that we know here. Okay, so let's do this without doing any math. Okay, just kind of give you a sense for what's going to happen here. I'm going to do this in blue. Okay, this one is going to have to push against that one. Okay, it's going to have to push against that P. Okay, now based on that, this whole thing is in compression, so it's pushing that way. Okay, so now that we know that's in compression, Well, that means this thing right here is pushing on this joint in this direction. Okay, so because it's pushing on it in that direction, if I imagine this one has to pull against it, if I imagine a coordinate system that looks like this, right? Okay, so if I kind of turn my coordinate system, then this one has to, so this one now is pulling. So this is in tension, this is in compression. Okay, now both of those have this force and this force are going in that direction on this joint. Okay, so probably the things in this joint are going to be going this way and this way, probably, maybe. We can't tell that much actually, but the net of these two forces is going to be that way. Okay, and that's about as much as we can tell from that. Okay, at least without putting in numbers. Okay, I can go over here to this AX and this AY. Well, we don't actually know what the signs are on those. Let's see. Actually, if we were to solve this, sum of the forces in the X, sum of forces in the Y, some of the forces in the X are going to tell us AX does not exist because it's the only, oh no, that's not true because we have an external force here, P. Okay, so P is going to the right. So AX is going to go to the left. Okay. A and O are both going to be vertical. All right. So if I go in here to this joint, right here, I can tell that since AY is up, this thing is going to have to push down on that joint, which means it's going to push, it's going to be in tension. No, not tension, compression. Okay, because it's going to have to push down on that joint. And since this one, its X forces in this direction and AX is in this direction, then the force in this thing is going to have to pull to the right. Okay, like that. And that's going to be in tension. Okay. So this is like, I don't want to get too far into this, but it is good to try to build this intuition when working these problems. Okay, I can usually look at a truss, and because I've worked in 10 million of these in my lifetime, and I can kind of just like mentally start picturing what's in compression, what's in tension. And so I think it's very helpful for you, like when you're looking at these things, to try to imagine bending these things and curving these things and like what these forces are going to be. It's a very useful habit. And also getting rid of zero force members just because it helps you. In this problem, if you couldn't identify the zero force members and I asked for all the forces in the joint, as you did all the equations, you would work through and you'd get a lot of joints where you'd be like, oh, sum of forces in the X equals 0. And you'd only have one force and you would go, oh, equals 0. And so it wouldn't be the end of the world, but you would just end up with a lot of extra equations. So it's nice if you can identify the zero force members before you start because it saves you some time. Okay, so I'm gonna, we don't have a lot of time left. Whew, and the coffee's hitting me and I'm getting crazy. Hopefully y'all don't sense that I'm crazy. my PhD advisor used to get hopped up on coffee and then he would teach and it was, you felt like you got hit by a truck afterwards. I hope to never like hit you guys with a truck. Let's see. I'm going to go to question number 9. And I'm just going to kind of sketch it out and we're going to do some strategy here on number 9 because there's not really a lot of time. But here's number 9. And let's do this. Okay. I had intended to work 3 of these, but it looks like I'm not really going to get to fully through a third one. But hopefully kind of slowly walking through one is better than, that first one is better than working, I mean, I guess the procedure for the joints is, rinse, repeat, rinse, repeat, rinse, repeat, rinse, repeat, rinse, repeat. And again, for some reason, I really like it, even though I guess it's probably a little tedious, but I just really enjoy it. Okay, so this one, what are they ultimately going to ask for? Oh, they ask for the method of joints for this one. They want to know everything. Okay, so this one looks like this. Here's Q. Here's P. And the numbers are equals 62 kilonewtons and Q equals 49 kilonewtons. Okay. Now we've got a joint here. I mean, not a joint, coffee. BY and BX, what do they call those things? Oh my God. Guys, I should not have drinking that coffee. Okay, I'm gonna have to eat something. Anyway, all right, so this one, first thing I want you to recognize right now is that CY is gonna be up. Okay, hopefully you can see that, because if you were to imagine putting your pin right here and imagining which P and Q are both causing this thing to rotate around that joint in this way. So CY is going to have to push against those and make it rotate that way. Okay, so that's the first thing that you should be able to see. Okay, and then BX and BY, well, BX, we know BX right now without having to do any work. Okay, because if we sum forces in the X on this whole thing, well, BX has to be the opposite of P. Those are my only forces in the X. So BX is actually going to be the other way. It's going to look like, I don't want red. It's going to look this way, negative 62. So 62 kilonewtons. Okay, hopefully you guys can see that.
Can you please repeat this? Can you please repeat this step?
Yeah, so what I did mentally is so on the whole thing, I said, what are the sum of the forces in the X direction? I've got P, positive 62 kilonewtons, and I had BX like that. So I said plus BX equals 0. So I said BX has to equal negative 62 kilonewtons. Does that make sense? I think
Yes.
that was
so
okay.
BX should be on the other way. So it's gonna be
Yes.
positive. Okay, got it.
So I did this and I said, okay, well, let's go ahead and include that information here. 62 kilonewtons, like that. And then to get CY or BY, either one, I need to sum moments. And you can do that wherever you want. In this case, if I want to solve for either of those two, I'm going to make my point either at point B or at point C. To me, B is just the easiest. So to me, so I'm going to do the sum of the moments around point B equals 0. And so why? Because that gets rid of both of these forces are not in my equation. So I'm going to have CY times its moment arm. I guess I didn't give you the geometry here. What is the geometry? 2.4 and 0.7. So 2.4 meters, 2.4 meters, and 0.7 meters. Vertical, 0.7 meters. So if you know your triangles, this is a 7, 24, 25 triangle, which is not as commonly used as a 3, 4, 5. But if you know your triangles, this is a 2.5 meters. You could just do the Pythagorean theorem to get that. But it is nice when you start noticing these things. But CY times 2.4 meters. Okay, and that's causing things to spin. Let's see here. So again, fingers, X, palm, Y. Okay, positive Z. One nice thing about trusses is they're always in 2D. I mean, obviously you can work a 3D truss. 3D trusses exist in the real world, but they never show up in status class. And so let's see here. So that positive Z. So CY is causing things to spin in that direction. So that's a positive number. And then we've got P. Let's see, which P is going to be causing things to spin this way. So is Q. Okay, so both of those will be negative because they're going the opposite of that Z. So minus 62 kilonewtons, minus 49 kilonewtons, and we need moment arms. Okay, equals 0. And so the moment arm for 62 is, well, let's see, we're going to back this thing up right here. Okay, that's 0.7 meters. And then the 49, let's see, its moment arm. That one's actually nice because it lines up. It's right here. So that's 4.8 meters. Okay, so then we just got to do that algebraically and figure out what that is. Let's see, 62 times 0. 0.7 plus 49 times 4.8. Then we'll divide that by 2.4 equals 116.08. So CY equals 116 point. You know, I wish they would just have the numbers work out to a pretty number. Okay. But okay, sorry. I blame, oh my God. Sorry, I really can't handle caffeine. That was a real mistake. All right, so let's sum the forces in the y direction. So CY is 116.08 kilonewtons. The Q is 49 kilonewtons, and the BY is the last force equals 0, and BY equals whatever that equals. So you should notice, by the way, that I'm getting a little quicker here with solving these things. Hopefully you're getting more comfortable with that. And this is getting a negative 67.083 kilonewtons. That's the reactions right there. So, you know, the first step of these usually is to get the reactions. In this frame, you almost certainly need the reactions before you do anything else. Okay, so we are, okay, so once you've done that, this thing is a lot easier. So I'm going to start erasing some things that are kind of in the way. I don't need all this business. Okay, once we have the reactions, so BY is negative. So it's right here. So that's 67.082 kilonewtons. CY is 116. By the way, I'm going to go ahead and teach to 11. You don't have to stay if you don't want to. Obviously, you don't even have to come if you don't want to. But I want to finish this problem because I want to show you how I do the method of joints. Okay, so this is going to be a little bit quicker than the last one. Among other reasons, it's a smaller truss, so that helps. Okay, I want to note that there's a temptation to make this a zero force member, but remember we've got an external force on it. So this vertical force is actually really easy. So here's what I'm going to do. Okay, let's see, I'm going to draw these all in red so we can see them. Okay, it is nice to have a different color. Okay, if you can do this. Okay, and I'm going to erase all this stuff. So I'm going to show you how to do this because this is how I do it so that it doesn't take so long. Okay, oh, I'll rewrite that. Q is what, 49, did we say? 49, I think. Okay. So what I do is I do all of my free body diagrams on the drawing itself. So this is 49 kilonewtons. And so we can start anywhere. The easiest place to start, well, maybe it's not the easiest because we can't resolve it all the way. But one of the easiest things that we can do here is I can look at this. So I'm going to go joint by joint. So I'm going to look at this joint right here. Okay, one of the things we can tell right there is I'm going to do this in my head. So mentally, I'm summing forces in the y direction. So notice I've got 116 kilonewtons going up. So down, I have to have 116 kilonewtons. Okay, which means that up here, I've got 116.08 kilonewtons pushing up into that joint. So this is 116.08 kilonewtons. Okay, has to be. No other option. Okay, now I don't know about these, you know, anything about the x direction in that force, so I'm gonna have to come back to it. Okay, so let's go back. Let's go to this joint right here. Okay, and usually I start on one side. This was just so obvious to me that I wanted to, like, I got overexcited. So I can start either at this edge or this edge. But I'm going to tell you right now that this edge is easier because it only has one force. So we're going to start at that edge. Okay. And what I'm going to do here is I can go in the x direction or the y direction. It doesn't matter. Except for the fact that in the x direction, I don't have any information right now. So we're going to start in the y direction because I have a y force here. And I know there's a y force in this one. And I know that it has to pull upwards because this one's pulling downwards. There's only two forces. So this one has to counter that one. Okay, and so that means that this one is in tension. So it's going to pull on both joints. Okay, and the vertical component of this thing has to be 49, right? Has to be. So I just need to figure out, well, I can figure out its horizontal component if I want. Okay, I can figure out the horizontal if I want. But the most important thing is the diagonal component of that. So I just need to do some trig here. So I know a triangle. I know this is 49 kilonewtons. and I need to know what this side is. And it would be nice to know this side because that's going to help me out later. So we kind of need an angle here, right? And so, well, we can get this angle. We'll go ahead and do the trig. I think most of you are probably more comfortable with the trig. So I'll do theta equals the inverse tangent of the opposite, 0.7, over the coffee, 2.4, the adjacent. Sorry about my coffee buzz here. It's not treating me well. I'm actually like shaking. Inverse tangent of 0.7 divided by 2.4, 16.260, 16.260 degrees. Okay, so to figure out this triangle, that's this angle right here, 16, so this is theta. Okay, so to figure out this triangle, I'm gonna go, how do we get this? Get that 49, so that's the our opposite, so we're gonna do the sine of theta equals the opposite, 49 kilonewtons, over the hypotenuse, which is this one right here. So this is AD, is the name of this force, over AD. Okay, so I'm going to plug in that 16 right here, and AD equals 49 divided by the sine of 16, whatever. So the sine, sine of this number right here equals, we're going to raise that to the -1, and we're going to multiply that by 49. So that gives me 175 kilonewtons. Okay, so this side of this is 179 kilonewtons. 175 kilonewtons. And then I'm going to go ahead and get this side right here because it's going to be useful for me. I know this from having done these problems many times. And so that one's going to be 175 kilonewtons. So that's, this is going to be 175 times the cosine of that angle. Okay, again, I'm just going to plug in 16.260. So 175 cosine 16.260 is going to give me 168 right there. So it's going to be 168 kilonewtons. We got a problem with nice, pretty numbers. Okay, so I can go up here and I can say, okay, well, this thing is 175 kilonewtons. Okay, and I know from my drawing that that I've drawn it so that it's actually tension. Okay, and so from that, now I can go and I can do the sum of the, so now I'm going to go and I'm going to finish this joint off by looking at this one and do some forces in the x direction. Okay, and I've got this x component force right here, which is 168 kilonewtons, and it's going to the right, which means this one has to go, excuse me, this one's going to the left. So this one has to go to the right. And I'm going to say, okay, well, this one has to be in compression, and it's going to be 168 kilonewtons, like that. Okay. So now I'm going to keep powering through. I'm going to go back. I'm going to look at this joint right here. Okay. Earlier, I did some forces in the y direction. Now I can do the sum of forces in the x direction. And I've got this one pushing, this 168 kilonewtons is pushing to the left on that force. So this one has to push on the right, sum of forces in the x direction, like that. That is 168 kilonewtons. Okay, hopefully this is making sense. And it's kind of logical, but you just have to kind of keep fighting through. So now at this point, we know everything except for this one member right here. And we can use either joint for this. So I can either use this joint up here, or I can use this joint down here. And it just depends on which one you think is going to be easier. Okay. Now, one nice thing about this is a way to check your answers is you do both joints. You do this joint, and then you do this joint, or vice versa. And you should get the same answer. And if you get the same answer, then you go, okay, the odds that I screwed this problem up are very, 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 very slim. Okay, so we're just going to do one of them because we're out of time here. And we're going to do this one because I already know all the components. I know of this force right here. I know that on this joint, I've got an upward force of 116.08. And I've got a force to the left of 62. Okay, Oh no, I forgot this one. Oh, never mind. So actually, plus I've got a force here, which looks like it's 168 from over here. And I've got a downward force of 49 kilonewtons. Okay. So net to the right on this thing, I've got 168 plus 62. So what is that? 170, 230 to the left. And I've got net up this, 116 up and 49 down. So 116 minus 49, clear. 116.8 minus 49 equals 67.08. Down, that's a net 67.08 kilonewtons. Okay, sorry, my head is like, okay. I've made an error here somewhere. Okay, because that is a net force going this way. And this thing can only push in this direction or pull in this direction. So it can only do one or the other. So I've made an error. Okay. I'll have to clean this up and solve it for you later. But that's the idea of how I do it by joints. I think I wouldn't have made this error if I hadn't drinking that coffee. I'm going to apologize. So let's call it, and what I'll rework this one, and I'll do a video for you guys, and I'll rework it to get it correctly. But this is how I do trusses in order to in order to kind of limit the amount of time spent on the joints. And I find it to be a little bit elegant. So anyway, thanks guys, and I apologize for that error. And next time I won't drink coffee. I don't know if you can tell that I'm totally like, definitely had too much, and it took a while to kick in, but I'm like I'm sorry. I'm like sweating here. I'm shaking. I should not drink caffeine. Anyway, thanks guys. I'm gonna rework this one and give you a video. I'll do it sometime today. Also the other video from last Wednesday, I finally got it to load. I think it probably loaded late last night. So that's available on Moodle if you want it. Okay, I'll see you guys. Actually, I won't see you all on Wednesday because Wednesday I'm just gonna do the retake for the people who want to do the retake. So thanks guys. Jansen, if you want to hang on and we can talk about whatever your question was. But see you guys.
Thank you so much.
All right. See ya. Hi, Jansen.
Yeah. So whenever I went to do the survey the other day, I didn't include my name on it.
Oh yeah. I got your email. So
Yeah.
I included you on there.
Okay. All right.
Did you get my follow-up email?
No, I didn't get it. That's why I was asking.
Well,
I don't know if I didn't get
okay.
it.
I'll write your name down and I'll make sure to send it to you. What's your email address? Just to make sure that I type it in right.
It's jjpelleg@uno.edu.
Okay. I think I might have sent it to @myuno.edu. Does that matter? The my?
I'm not sure. I don't think it does.
Okay. Yeah. So this is all being recorded. Are you okay if this makes it onto the official recording, or do you want me to get rid?
That's fine. It doesn't matter to me.
Okay. All right. Because otherwise it'll take me a little while, but I'll figure out how to cut off the last 30 seconds of this video.
It's fine. It doesn't matter.
Okay. How you doing otherwise? Anything I can do to help you?
I'm doing all right. I've been doing a lot more extra practice problems. So.
Okay. Yeah, your work on the last exam was very well organized, and so once I think you'll be fine. So let's knock this one out.
Yep.
Just let me know if I can help. Okay.
Okay. Well, thank you.
Okay. Okay. Yeah. All right. I'll send you an email shortly.
All right.
All right. See you. All right. My God, I'm really shaky. Okay. Let's stop recording here. Maybe if I eat some food, let's see, stop share.